So we have all been dealing with forces all our lives. Up until now, we dealt with motion. And one of the things that we dealt with in our motion was we didn't care what was causing the motion. We just knew we were looking at our acceleration and our change in distance and our change in velocity. So basically what we've covered so far is we've covered vectors. We've done our kinematics. We've defined acceleration as a change in velocity with respect to time. We've defined velocity as a change in position with respect to time. And we had our kinematics equations. We had our three kinematics equations, and we worked through those items. And we also said that we had independent motion. That meant that if I was tossing my basketball and it was curving like this was our projectile motion. We could come at any point in here, and if this is my vector, I could break it up into its x component and its y component. So we could actually break those apart. But we know a few things because we've played these games a long time. So if I have two people here and my artistic things are really entertaining, and I have my flag and we've got a tug of war, if this person is pulling in this direction and if this person is pulling in that direction, if they're pulling at the same magnitude, okay, they're both pulling at the same magnitude, nothing's going to happen. Nothing will happen because they're canceling each other out. And this is our pull. And so we can think of this pull as a force. And we can look at that if I'm pulling on something, it's a force. We also know that if I have a big object and I'm going to put it on some wheels here, and I'm applying something along the lines of getting it to move, and we've called that thing a push, I'm applying another force. So if I'm looking at a simple explanation for what a force is, I know that force is related to a push or a pull. And these we're going to actually call contact forces. I'm physically in contact with the rope, or I'm physically in contact with the object that's there. Now, one of the things that you guys did is you looked at changing the mass of something. And for the lab that you guys did, you did this. You've got a plot, and you've got a plot is equal to force, and you have a plot that's an acceleration, and you got all these data points. Right? Got all those data points. And if I have all those data points and I drew my best fit line through there, we know that the force is going to be proportional to the acceleration. Now, if this was my IO lab, and my IO lab is about 292 grams, if I did this, the slope of this line is going to be somewhere in the neighborhood of 290 grams. That's where it's going to work out. That's what we've got. Now, what happened if I put more mass on there? And well, when we put more mass, what you saw was that the slope changed. Right? And you may have gone in and you may have calculated that slope changed. And now let's say that that's like 340 grams. So in order to do something, we know that the force is changing, and we are actually talking about the greater the mass, I have a greater force. And mass relates to this idea of inertia. Okay, that relates to this idea of inertia. The more mass I have, the more push I have to get it started, the more all of those lovely things that we have to have in there. So I have my inertia that comes in. So mass is related to inertia, and we know that there's a relationship between my force and my acceleration. But what we're also going to do is we're going to look at what happens if I'm in space, and we've seen this happen all the time, right? If I'm in space and I toss a ball and it's moving at a velocity, we know that that ball is going to keep moving until it hits something. Well, the closest thing that we can do on Earth is we've got to get something that's not very frictionless. It doesn't have a whole lot of friction. And I can do that. And if I think of a hockey puck, we know that it's going to continue sliding across the ice until it hits something else. And this gives us Newton's first observation. Or what we call the first law. An object in motion will remain in motion or an object at rest will remain at rest unless acted upon by another force. So we're familiar with that. We've played with that. We've used it. We've experienced it in our cars. If I'm sitting here in my car and I've got my car's going this way, and all of a sudden I screech to a halt, what happens? Everything on my front seat goes forward. It's going to stay in motion because there's nothing holding it back, and it's going to continue to go forward until it hits the dashboard. So we know those things that are happening. Now, I'm going to go to Newton's third observation. I have a wall here, and I'm pushing on the wall. The wall's got to do one of two things. It's either got to move because there's a force that's being applied to it, or it's applying a force back. And what this means is that forces come in pairs. Or we also can say that for every action, there is an equal but opposite reaction. And we know this for a fact because if I have a rocket, right? I have a rocket, and my rocket has got the flames coming out the back. The rocket's going this way and my flames are going that way, and that's what's actually pushing my rocket to go forward. So we know that that happens. Well, the way our book talks about Newton's second law is we kind of are telling you a little different. You know, it's kind of like going to chemistry class and we tell you that there are 3 states of matter, but then we're in physics class and we tell you there are 4 states of matter. And as you get into dealing with other things, we're going to tell you there's more than 4 states of matter. It's somewhere between 8 and 15. Yeah. So we're always doing things and we're always bringing things up. And that's what happens with Newton's second law. In the materials that I have in Blackboard, you can actually go and see Newton's notes. They're all digitized and you can actually look at them and you can actually get into his Principia and actually look at it. You can see how he's looking at Kepler's laws and bringing all that back together, which is really cool. But what you do see is that that's not how Newton said his second law. So the second law, what Newton said was that I have a force is going to equal a change in momentum. Now that's an interesting idea, and we don't get to momentum until after we come back from break. But the idea behind momentum, and I'm going to go ahead and tell you what momentum is. Momentum is defined as the mass times velocity. So it's a vector quantity, and it's going in the direction of my velocity. And Newton said that force was equal to a change in momentum. So if I think of my hockey puck example, when the hockey puck comes in and hits the wall, it has a change in momentum because it's going to rebound off the wall and we get that rebound. We get a change in momentum. Well, if I do this, my force, and we're going to look at this, my change in momentum, actually, force is equal, this is actually impulse. Sorry, I left something out here because I'm going, something's missing. An impulse is the force times the time that's out there. So I have a change in time. There's my impulse. My impulse is equal to a change in momentum. And my impulse is the force times its time that it's being applied. And if you're a soccer player, you understand the difference, because if I give it a quick jab, I have a different impulse than if I do a little tap. And the longer I'm in contact with my ball, the change I'm going to get. So this impulse is my force times my time, and there's my change in momentum. So I'm going to play a mathematical trick. I'm going to say that my force is now equal to a change in momentum over a change in time. That's reasonable. That's reasonable. Now, to do this, this actually expands out. Basically, what this says is that I have my mass times my change in velocity over a change in time, plus my velocity times my change in mass over a change in time. We know what this is because we've been playing with that since early on in the semester. So this is my mass times my acceleration. And then I have my velocity times my change in mass times my change in time. And I've got this weird term over here that's a little different than what we know as Newton's second law. And why? The idea is why? Well, if I'm dealing with balls or hockey pucks, there's no change in mass. If there's no change in mass, so if my change in mass is equal to 0, this term goes away, and now I get F is equal to the mass times my acceleration. Now, these are vectors, And what we're actually also saying is that this is the net force. We have to account for all the forces that are acting on an object. And this is the second law that we see in the chapter. But this term that's hanging out over here, this is what we call rocket science. Because if I've got a big rocket that's going to the moon, I do have to worry about this change in mass in order to explain what's going on. But this is the one that we're going to use for most of the chapter, this one right here. My net force is equal to mass times acceleration. There are a couple of other things that we have to talk about in terms of forces. One is if I have my hockey puck, right? There's my hockey puck. And it's sliding across the ice. We know eventually it stops. Why? Because there's another force that's being applied. And that's the force due to friction. And friction forces are very important. We can't walk across a floor without a force due to friction. Now, if I do this, if I take a block and I put it on a plane, I can raise this plane and the block will sit there and it'll sit there and it'll sit there, and then all of a sudden it starts to slide down. And that's how we can actually measure friction. And that's what you guys are going to do in the lab for next week, is you're actually going to measure friction. But it's going to depend on whether or not I've got frozen rubber over ice or I have a wooden block on sandpaper. I'm going to get this, what we call a coefficient of friction. All right, I get a coefficient of friction. And that's kind of an interesting thing. And that's going to be actually be able to be measured, and we can actually do that. But I also have a coefficient of static friction. That's what's going to hold it in place. And then I have a coefficient of kinetic friction. And that's the friction that I experience when something's moving around. And my static friction is generally greater than my kinetic friction. But we can actually work with these things. Now, let's draw on the tabletop here. And so I've got a tabletop. And I've got a big object that's on my tabletop. And it's got a mass to it. It's not moving, but Newton's third law of observation says, well, I got something that's dealing with it. Well, one thing that we know is if the table wasn't there, it's going to fall. Because we've played the dropsy game for a long, long time. Right? We've played that dropsy game all the time. But the reason it's not moving is because I have another force that's opposing this. And this is the weight. The force downward is the weight of my block. The force upward, we're going to call it N, and we're going to call it a normal force. And it's normal because it's perpendicular to the plane. Basically, that's why we call it the normal force, because it's perpendicular to the plane. So we get our normal force because this is coming from Newton's third law. Okay, that's where that's coming from. Well, for my force due to friction, what we have discovered is, and we're going to use a script F for my force due to friction, is that's equal to whatever my coefficient of friction is times the normal force. So this is one of the things that we have to take into consideration when we're talking about forces. Now let's look at our plane here. There's my angle of my plane. I have an object here. The weight of the block is always going to be towards the center of the Earth. And we're going to get to that here in just a second. And then I've got a normal force that's working against my block. But this, I've got to be able to work my problems so that I can work along the plane or perpendicular to the plane. So what I'm going to end up doing is I'm going to break out my weight. So this is my weight, and this is going to be the weight in the perpendicular direction, and this is the weight in the parallel direction. But this angle and this angle are the same. So if I'm doing the weight parallel, that's going to be equal to the weight sine of my angle. If I'm doing the weight perpendicular, that's the weight cosine of my angle. And so you can break up your components into its different parts. So that's one of the interesting things that we got to deal with. So let's go ahead and do Newton's other law, and this is the universal law of gravitation. Okay. And we have to kind of take a couple steps back. And it's really cool right now to take these couple steps back. Because we're going to come from Kepler. And these are going to come from Kepler's laws. And Kepler's had 3 laws. The first law that he said is that here's the sun, and here are our planets, or a planet, we'll just have a planet, that our planet is going to orbit around the sun, and this orbit will be an ellipse. With the sun at the center, the sun at one of the focuses. So if I had the focus there, here's my planet, there's the focuses of my ellipse, and my orbit's going to be an ellipse. Turns out that Venus is nearly circular and Earth is nearly circular. Okay? But that's why we talk about the aphelion, because it's not quite a circle, and in the, where we are, that's where we're furthest away or we're closest to the sun, we end up with those, but we're following an ellipse, and our ellipse just happens to be very nearly circular. So that's the first thing Kepler said. The next thing Kepler said was, as I sweep through, as the time that it takes to go for here, the areas of these triangles are going to be the same. And he said that the period of our orbit, the period squared, is roughly proportional to the radius cubed. Kind of an interesting observation. These areas are the same. Our period goes like that. And all of this was to explain how Mars, or what we saw with Mars, and we get retrograde because if this is the Earth and Mars is out here, as we move around, Mars appears to do this loop-de-loop thing in the sky. Now, we're about to have something really fun happening on Tuesday morning. We're going to get a lunar eclipse. What's going to happen is here's the sun, here's the moon, or here's the earth, and the moon is going to come in behind and it's going to enter into the shadow of the earth, and it's going to turn colors because it's going to be in the earth's shadow. So Monday morning between 5 and 6 a.m., you may want to get out, or Tuesday morning, you may want to get out and actually look at that, but we're working with it. So anyway, what's happening here is Newton used Kepler's laws and he wanted to explain the Earth-Moon system, and he wanted to figure out why it was doing what it was doing. And after he did a lot of calculations, he showed that the force was going to equal to some constant that we call G, the mass of the Earth, the mass of the moon, divided by the radius squared, was going to give us our explanation for why the moon is going to be there. And that also explains tides because the masses have an attraction. And Cavendish actually did an experiment to show that. But now we write this as mass 1 and mass 2 because you can even show it with bowling balls. Bowling balls will actually show this behavior. But if I write this for the Earth-Moon system, I get the force is equal to gravitation, mass of the Earth, radius of the Earth squared times whatever object. So if I think if I've got my Earth here and I have a little itty bitty object like a ball on top of the Earth, this height here isn't much different than that height here, and this equals our acceleration due to gravity that we see at the Earth, and this gives us something that we call a field force. So we get field forces and contact forces, and we work through those. So weight is going to equal our mass times our acceleration due to gravity, and that is a force. And this is how we get our concept of weight. And if I do this, this is in kilograms, and this is in meters per second squared. And so now I've got a kilogram meter per second squared, and we're going to define that as a Newton. And that is a unit of force. So we have a unit of force. And our weight relates to this. We want to do one more thing, and this is going to be Hooke's law. And basically what Hooke's law says is that if I start with a spring and then I put a mass on it and I get a stretch, this is my stretch, and this is my weight. He showed that the force was proportional to the stretch. And we can do Hooke's law is this is minus some constant times the stretch. And we say that equals X. And this is what we call a spring constant. This is because it's a restoring force. And this it lets us look at forces due to springs. Now, in Blackboard, I've done these a little differently. I've explained it a little differently, but I wanted you all to see all of the equations that we're going to play with in this chapter before I started doing problems. And I'm kind of giving you a little bit of background as to where they are. But I do encourage you to go back and look at those individual videos because we've walked through a lot of different things. But I wanted you to kind of have a summary of everything together so that we could work through it and work through a variety of problems. So now what I'm going to do is I'm going to kind of go back and we're going to look at motion from a different perspective, and we're going to actually start working some of the problems, but now you've got all those different parts. So first of all, we have to go back to the idea that a force is a vector. So if I have an object here, I'm just going to use this as a weird boat, okay? And I've got a force of 10 newtons pulling that direction, and I have a force of 20 newtons pulling that direction, we know that the boat is actually going to go kind of over there. We can actually look at it a little differently here. If I have a boat that's going across the river and I've got the river flowing here, I've got a force that's acting on my boat. The motor's causing the boat to go this direction, right? The motor's causing the boat to go that direction. I've got a force on that direction, and the boat's actually going to kind of go something like that. Because we've experienced those things before. So my Newton's second law is that the sum of the forces is going to equal my net force. And we can figure out that that's going to be the mass times the acceleration. So let's give our boat a mass. We're going to say our boat is 50 kilograms. Because this is just an experiment here. And we want to figure out the direction of the boat. So first of all, we want to find out the resultant force. Well, guess what we got to do? We got to break this up. I got to give you some more information. We're going to say that this is 20 degrees, and we're going to say that that's 40 degrees. Okay, so now we got to do our two components. This is going to be 10 sine of 20 degrees. And that component is 10 cosine of 20 degrees. This one, I'm going to go ahead and do this in red. This is 20 times sine of 40 degrees. And this red one is 20 times the cosine of 40 degrees. Okay. So if I come over here, I've got the sum of the forces in the x direction because they're independent. So we know that my x direction is going to be 10 cosine 20 degrees plus 20 cosine 40 degrees is going to give me my x component for my resultant force. And this is 9.4 plus 15.3. It's going to give me 24.7, and that's in newtons, and that's the components in the x direction. The components in the y direction is a minus 20 sine of 40 degrees plus 10 sine of 20 degrees. I get a negative 12.8. And I get a positive 3.4. It's going to give me a negative, gives me a negative 9.4. So we know what's going to happen there is my resultant force is going to be somewhere over here. And I'm going to actually write my vector as 24.7 in the I direction minus 9.4 in the J direction. And if I want to find the acceleration, I'm going to take my force divided by the mass, and that's going to be 20, or if I do my 9.4 divided by 50, this gives me a negative 0.9 in the J direction. 24.7 divided by 50 is 0.49 in the I direction, because I can calculate what my acceleration is by looking at my force. So that's one approach to the problem. One approach to the problem. We already did weights. And third law. Then our friction forces. Okay. What I think I'm going to do at this point is I think next week, what we'll do is we'll do a whole bunch more examples. You do have a lot of examples in Blackboard. I would encourage you to go out to the survey for this week and respond to that and say, hey, I'd really like you to work this kind of a problem or that kind of a problem. And I will do that as part of the stuff for next week. But what we'll look at is an Atwood's problem. We'll look at a friction problem, and we'll look at a couple of other, a spring problem. But I want to give you a chance to kind of play with this first and then ask some questions, and then we'll do a lot more examples. But if you need more examples, they're already out there. So any questions? Because I know I went through stuff pretty fast.